All right, in this lecture, we jump into learning about the Earth's atmosphere. So, in physical geography, we cover systems. We cover four very large systems. The first system that we look at is the lithosphere. The lithosphere, we talk about the rock cycle, we talk about weathering, mass wasting, volcanoes, earthquakes, and the like. And then we start talking about the hydrosphere, and we start including the water in with the lithosphere, how water moves, how water creates and moves and affects the landscape of the lithosphere, right? The surface of the earth that we live on. So we've gone through two systems, the hydrosphere, the place where the hydrosphere and the lithosphere meet, and we've gone over the lithosphere. And now we enter into the atmosphere. Now remember, all of these systems that we're talking about, they're all circular in nature. None of them are linear. The Earth has not created linear systems. The Earth has created circular systems. So you'll also notice that all of these systems work in conjunction with one another. So the Earth's atmosphere is also included in the hydrosphere, right? So the hydrosphere means water. It's basically a fancy term for the water cycle or the movement that moves, the cycle that moves water. Now, when water is evaporated, physical water as a liquid, it's evaporated and it turns into its gaseous state. At that point, as humans, we're unable to see it, right? We're unable to see it. And then when it evaporates where? Into the atmosphere. So that is one example of how the hydrosphere and the atmosphere interact and overlap. Now, one of the most important things that we'll go over in this overview in this lecture in talking about the Earth's atmosphere is insulation. We've discussed a little bit about insulation in the beginning of this course, except this time we're going to peel off more of those layers and then dive into talking about solar energy and the global energy system. Now, what is insolation all over the globe? Insolation is the amount of energy received from the sun. Now, I like to say that we eat sun. Well, we don't necessarily walk outside and eat sun. We eat things that eat the sun. Also, the sun is what fuels all of our weather. The sun fuels the weather and therefore it fuels precipitation. The sun and the sun's heat and the sun's energy fuels evaporation of water into the atmosphere, which then perpetuates this cycle of bringing us water. What as humans are our fundamental needs: air, food, and water. So this energy that's received all over the globe is what we call insolation. And it comes at a rate and it varies each day and over a year, and it varies by latitude. So we've already learned that the Earth's equator, so at 0 degrees, that is the area of the Earth that receives the most constant, the most intense amount of energy and insolation concentrated than any other part of the globe. The farther away you get from the Earth's equator, the less insolation you receive. And I like to think of it as if you would take a flashlight and if you would shine it directly down on the floor, you're going to be getting the most concentrated amount of that energy from that flashlight if you point the angle straight down to the floor. So this is the type of insolation that the areas around the equator are receiving. They're receiving the most intense amount of insolation throughout the day and throughout the year, because this is how the sun's rays are contacting the earth at that location. Now, The farther north and the farther south, so the farther you get away from the equator, and the closer, and as you move toward the poles, that angle of the sun is going to change. And so this is why we talk about latitude in terms of degrees. So this concentrated amount of sun is now going to be spread out over a wider area. So in order to receive this same amount of sun, it's covered by a larger area. And then again, the higher you get in those latitudes, either north or south, as you move toward the poles, the sun's rays, this angle, is going to change. And therefore, you're going to notice that now, since the angle of the flashlight has changed, therefore the sun's rays, you are now taking the same amount of energy, but now you're spreading it out over 2 times the surface area. So if you think about what they can farm, let's say in Alaska, well, they can't farm much. Why is that? Well, yes, it's cold, but why is it cold? One of the reasons why it's cold is because areas that are farther away from the equator receive less concentrated sun, whereas the equator receives higher concentrated amounts of the sun's energy, which we call insolation. Well, and you might say to yourself, well, you know what? What about the times where the North Pole receives 24 hours of sun? Well, they do. They absolutely do. They might receive 24 hours of sun. What they don't receive is very strong amounts of insolation because of the angle they sit at relative to the sun's rays. And that is why we see these seasonal changes, for example, as well. So here's the sun, and here is the orbit, which we call an ellipse. And oddly enough, the December solstice, which is December 22nd, is actually when we are nearest to the sun. Now, in the northern hemisphere, we call this our winter. So you might say to yourself, okay, so for that reason, why is it that when the Earth is closest to the sun, we in the northern hemisphere are during winter? Well, it's because it does not have to do with the proximity of the Earth to the sun. It has to do with the angle of the sun's rays. For example, if you're in the southern hemisphere during the December solstice, you're actually going into summer. And inversely, in the northern hemisphere, the angle that we're at is pointed away from the sun, or excuse me, toward the sun, even though we're farther away in the northern hemisphere, which is why this is the onset of our summer. And the southern hemisphere, their angle is pointed away from the sun, which is why this is the start of their winter. This is a reason why the tilt of the Earth's axis is the reason for the seasons. Without this tilt, there would not be this drive away or this angle, right, away or toward the sun. So the Earth is tilted on an imaginary axis, and this axis, the angle is 23.5 or 23.5 perpendicular to we call the plane of ecliptic. Why do we call it the plane of ecliptic? Well, out in space, there's no, for example, when you and I walk around, there's the ground. There's some sort of reference point. So if we were to cut the Earth in half, for example, in some area, we would call this a plane, a planar surface. So we need some sort of surface in order to reference or measure an angle from. So the Earth's axis is from this perpendicular to this plane, is our Earth's axis is tilted 23.5 degrees. And what does this mean? This means that we now encounter our latitudes both north and south of the equator. And as the Earth is tilted on this axis, not only do we have varied insolation rates based on latitude, we are also going to have seasonal changes as well. Here you'll notice that the latitude zones that they decrease in insolation from the equator to the poles. So, for example, we divide out the Earth into these regions. The first region we call this area in and around the equator is equatorial. Outside of that, between 10 degrees and 25 degrees south and north, we call that tropical. And between 35 and 25 degrees north and south, we call that subtropical. So, for example, Southern California, LA, Orange County, and San Diego are all between 25 and 35 degrees. That's why in those locations you can grow things like citrus. Citrus are considered a subtropical fruit. And that's why they can grow those things there. Now, the minute that you get north of Santa Barbara, all the way up to just about Canada, we call this region the mid-latitudes. The mid-latitudes are cities like San Francisco, Portland, Seattle. And past that, we have a small section called the subarctic, and then past that, we have the Arctic. And you'll notice these other delineations here in this next slide. Which brings us to a conversation about solar energy and the Earth's atmosphere. So outside of all of this, we actually have an atmosphere that protects and insulates us in a very perfect way, in a perfect way that humans and flora and fauna of Earth have all been designed around and adapted to living in and with. So what is the atmosphere? The atmosphere are layers of gases that surround the Earth. And you might say to yourself, well, where does the atmosphere start? Well, the atmosphere starts right after your feet. We live and breathe and move in the atmosphere. It's anything from the ground up. Because, right, we're breathing these layers of gases. Now, we might be in those lower reaches of the atmosphere, but nonetheless, it's the atmosphere. These layers of gases are held in by gravity, and these layers of gases protect and insulate all life on Earth. So the atmospheres are vital. Why are they vital? Because they protect and they insulate. And what does that mean? I want to tell you what that means. And we're going to start talking about the different layers of the atmosphere. The first layer that we have, the layer that we live and breathe and spend most of our life in, is what we call the troposphere. The next layer out we call the stratosphere. And in between the troposphere and the stratosphere, we have a boundary, and it's called the tropopause. Here's another image that will illuminate to you what happens within the troposphere and what happens within the stratosphere. You will also notice that this line here that we're looking at is called the tropopause. So what happens in the troposphere? Well, you and I and everything really that pertains to our life is here. Air travel, most weather occurs in the troposphere. There is some weather that will leak into the tropopause and into the stratosphere, but water vapor does continue to rise from the troposphere into the stratosphere as well. And we'll talk about one of the important reasons for the stratosphere in just a minute. Some of the most important facts about the composition of the atmosphere is that most of the content of the atmosphere, 97% of it, is within 30 kilometers or 19 miles of the Earth's atmosphere. So here, for example, we have a chart that goes through miles. So we've got 7 miles, 30 miles, 50 miles above sea level. Okay, so we have 97% of our atmosphere is it within 19 miles. So that brings us to about here. Okay, air density is going to decrease with height. So that's also why I like this image, because it's telling you that air is going to be more dense closer to the surface, which is one of the reasons why you've noticed that when you go into the mountains, it's harder to breathe. Because as you go up in elevation, the air decreases in density. So the troposphere is the lowest layer of the atmosphere, and it's where human activity and most weather takes place. The temperature usually decreases with height, and the temperature is going to decrease about 3.5 degrees Fahrenheit for every 1,000 feet that you go. Most harmful radiation is, let me see if I can scroll down. Most harmful radiation is absorbed prior to this layer. And that really is where the importance of the stratosphere is going to come in. And we'll talk about the stratosphere right now. So the next layer up above the troposphere is the stratosphere. So like I said before, we live and breathe and spend our lives in the troposphere. Then there's this boundary in between the stratosphere and the troposphere called the tropopause. The next layer up we have what's called the stratosphere. What are some of the characteristics of the stratosphere? Now, in the stratosphere, as you go up in elevation, the temperature actually increases. So this is a real difference between the tropopause and the stratosphere. Remember, in the troposphere, as you go up in elevation, your temperature is going to go down. Like when you go into the mountains, for example, on a hot summer day, the temperature goes down. Well, guess what? If you are in the stratosphere and you go up in elevation, your temperature is actually going to go up. Why is that? Well, one of the most important things that the stratosphere does for us as humans and all life on Earth is it houses at a very important layer called the ozone layer. The ozone layer is what we call O3. And what does it do? Its job is to absorb the sun's harmful rays. Now, harmful, what does that mean? Well, the sun is amazing, but the sun, our human life and all flora and fauna have been designed and adapted to life with the sun. But this ozone layer, what it does is it absorbs and it filters out anything that might be harmful to us or anything else trying to live and breathe and grow on the earth. So this ozone layer, what its job is to do is absorb ultraviolet radiation. Now, you and I live because of solar radiation, of good, positive solar radiation, right? That's necessary. But ultraviolet, which we also call UV radiation, is bad. It is not good. It is harmful to humans, it's carcinogenic, and it's harmful to plants and animals. So, this ozone layer is very, very important. It absorbs this ultraviolet radiation. It's one of the reasons why when you go up in the stratosphere, when you go up in elevation, it gets warmer because the ozone layer is working diligently and very, very hard to absorb harmful UV radiation. All right, so let's talk about the atmosphere. What's in the atmosphere? When we say that a certain amount of the atmosphere lives within 19 miles of the Earth's surface, what does that mean? Well, it means that we're talking about gases. Remember, the atmosphere are there basically layers of gases that are held in by gravity. What are these gases? Well, 70% of the Earth's atmosphere is actually nitrogen. And you might think to yourself, oh, that's pretty interesting, actually, because I had no idea. I thought most of the atmosphere was oxygen. Well, you're right, we do breathe oxygen, but nitrogen is one of those really life-giving and necessary nutrients, especially for us as humans as well. And the other thing is oxygen is very highly flammable. So 500 million years ago, the Earth's atmosphere was actually more oxygen than nitrogen. And now the amount of oxygen in the Earth's atmosphere has come down, and all life has really come into this nice, cozy place and evolved along with those changes. You will also notice that along with the 21% oxygen and 90 and 78% nitrogen, we also do have this 1%. We've got argon, other gases, and then we've got this small part for carbon dioxide. Now, carbon dioxide, which we talk a lot about carbon, right? And as humans, we breathe in oxygen and we breathe out CO2. And plants, what do they breathe in? Well, plants breathe in carbon dioxide. So if we breathe out carbon dioxide and plants breathe in carbon dioxide, it must be said then that carbon dioxide is going to be a necessary gas within the Earth's atmosphere. And that's absolutely true. We're going to need carbon dioxide. It also does a lot of other positive things that many of us don't realize sometimes. Now, what this slide is showing is that what started to happen is that as humans, we created a few chemicals. One particular chemical was called CFCs, and we call those chlorofluorocarbons. So before the days of air conditioning and refrigerators and things like that, we used, for example, big blocks of ice to cool down our milk, and we had swamp coolers before air conditioners. Well, CFCs, these chlorofluorocarbons, were created and they were very handy in helping us create refrigerant. CFCs are refrigerants. And well, what are we refrigerating? Well, first of all, on those hot days where it gets 100, what are we doing? We're refrigerating ourselves, guys. We're cooling down our environment. What else do we refrigerate? Well, we refrigerate our milk, we freeze our food, and there are chemicals in there called CFCs that were created. And then when we got rid of these air conditioners and we got rid of these refrigerators and freezers and things like that, they would leak out these chemicals called CFCs, chlorofluorocarbons. And what these they would do is they would actually rise up very easily, quite frankly, into the atmosphere and into the stratosphere, and they would break apart O3. And O3 is the ozone layer. And we started noticing that in the 70s and the 80s, this was a problem. Where like we're actively disintegrating our own ozone layer. And this ozone layer was built to protect us. We're like, oh my gosh, what are we doing? We're literally creating chemicals that are eating away at something that the earth built and designed to protect us. The nice thing is in 1982, we actually developed legislation to get rid of CFCs, which is great. And what you'll notice here is that we've got pictures of the ozone layer in the poles. So this is a picture of the Earth and the poles. And it's a satellite image of the ozone layer. And you'll see that red or yellow or orange is bad. So in 1982, we started noticing these gaps, right? And this is not good. And what we did in the 80s and the late 80s was we started banning CFCs, these chlorofluorocarbons that would float up and literally eat away at O3, which was our ozone layer. Well, in which the Montreal Protocol was all the countries of the earth came together and decided to ban CFCs together because the United States just couldn't do it on their own. Europe couldn't do it on their own. If we were going to get rid of these gaping holes in our ozone, which is built to protect us, we were going to have to do it together. So they got together in Montreal, Canada, and they decided to ban CFCs. And what you'll start to notice here is that over time, that ozone hole went away. So the cool thing and the really positive thing about the earth is that if we give it the opportunity to heal it and reroute itself, it definitely will, and it can. Another item that we put up into the earth's atmosphere are aerosols. Aerosols are tiny particles that are present in the earth's atmosphere, and they're so small and light that they float within the atmosphere. And things like this are ice, volcanic ash, any kind of exhaust, water vapor, dust, smoke, soot from forest fires or from your chimneys, for example. That's why you'll notice that If they decide to build any more homes in certain areas, most of the time it's very difficult to build a home that includes a fireplace because when you're burning a fireplace, you're creating more aerosols. And these tiny particles, other chemicals or other gases, can actually live or combine with these aerosols and create problems for the Earth's atmosphere. Which is what brings us into this global energy balance. And what is this? So, for example, if you have like a balance sheet, like you're like, okay, this is how much I make every month, and this is how much needs to come in because this is how much is going out, right? And what happens when you're over budget? Well, you might have to use a credit card, or you might have to owe someone money, or something just not great. Well, the Earth has something very similar as well. So there's a certain amount of energy coming in. There's a certain amount that gets absorbed. And then we have to make sure that there's a certain amount that leaves. Because what happens if we have all this energy and it comes in and none of it goes out? Well, not good. Excuse me. I feel like I'm getting a cold. What starts to happen is that sensibly our Earth is going to heat up, which it kind of makes sense. So, in this global energy balance, we have three ways that Earth's energy can behave. It can either be absorbed, scattered, or reflected. So let's scroll down and talk about how Earth's energy or how the solar radiation can be reflected. And one of those ways is a term we call albedo. Albedo is the proportion of solar radiation reflected up from a surface. So, for example, if you've ever gone to Disneyland on a really, really hot day, someone will say, wear bright colors, wear light colors. Why is that? Because different colors and different surfaces absorb solar radiation in different ways. For example, the color black has a very low albedo, which means that it has a very low reflectivity. What does that mean? That means that it absorbs a lot of solar radiation. So it's going to get very hot. What is one of the reasons that we have solar panels that are dark? Well, solar panels are dark because they absorb solar radiation. Now, inversely, you have snow. Snow has a very high albedo, which means it has a high proportion of reflectivity, which means that according to solar radiation, it's going to reflect a majority of that energy back up into the Earth's surface. Here you'll notice that in Los Angeles, they're building new buildings. For example, Los Angeles Harbor College. This is what we call nature in design. So the buildings are very light in color, correct? Because what we want to do, especially in places like LA, is there are lots of sun, lots of solar radiation, and it's getting warmer and warmer and warmer. So we want to build our buildings in lighter colors so as to reflect the sun's energy away from the ground and away from the buildings and back up into the Earth's atmosphere so that we're not warming our cities. We don't want to trap heat in our cities and create warmer environments than it already is. Now, also, what we like to do is create sustainable landscape and human constructs that are sustainable. So, for example, these solar panels are black. Why are they black? Because we want to make sure that they absorb the solar radiation, do their job, and create energy. The last concept I want to review with you is something that we call the greenhouse effect. And I know many people tend to think that greenhouse this and greenhouse is bad and greenhouse gases. I'm sure you hear those buzzwords pretty often. Well, the greenhouse effect, now, shocker, is actually a good thing. The greenhouse effect is something that the earth created on its own, and it's positive and it's good. Greenhouse gases are a natural process that the earth created on its own. Now, what does this mean? There are greenhouse gases, for example, carbon dioxide is one of them. Nitrous oxide is used in fertilizer and is not as natural. But methane is another natural greenhouse gas as well. The earth created these gases. The earth wanted them to be there. The only problem now is that as humans, we are actually creating more carbon dioxide and more methane than the earth had wanted to be there. So the earth created carbon dioxide and wanted it there, and methane for that reason too. Only problem again is for anthropogenic reasons and anthropogenic sources, we're creating more carbon dioxide and more methane than the earth needs. So we've overdone that global energy balance. It's too high. We're not balancing everything out like your checkbook. So remember, this greenhouse effect was created in order to insulate the earth and keep it nice and warm and toasty. Without it, our earth would be very, very cold. Carbon dioxide and methane have a very large capacity to hold heat. Now, the earth wanted CO2 there because they wanted to have just enough to help insulate the earth and bring equity to all parts despite latitude, right? Despite insulation. So the earth has amazing ways of making sure that it says, okay, guess what? There's high concentration of insulation at the equator, but maybe not so much at the poles. So in the earth's atmosphere, created gases, what we call the greenhouse effect. The only problem now is that, for example, we have too much CO2 and too much methane in the Earth's atmosphere. And again, these gases, their job is to trap and hold heat. That's what they were supposed to do. That's what the Earth wants them to do. The only problem is now is that as humans, we're putting up way too much methane and way too much CO2 and it's doing its job. It's doing what it's supposed to do. CO2 is supposed to absorb heat, methane is supposed to absorb heat, and they both absorb and hold heat. Methane actually absorbs and holds heat for up to 50 years. So think about the methane and the CO2 that we're putting up in the Earth's atmosphere right now. It's not like it's going to go away in the next 10 years. For CO2, it can hold a particle of heat for up to 30 to 40 years. Methane can go almost up to 80 years. So if we're putting up CO2 now, we're not going to see that CO2 degrade literally until you're a grandparent or a great grandparent. So now what technically has happened is that as humans, we have begun the negative part of the greenhouse effect, and it's called the enhanced greenhouse effect. The greenhouse effect that the earth created is good. The anthropogenic human aspect of the greenhouse effect, which we have enhanced it, is not good, and it is currently disrupting our climate. Remember, we have this global energy system and we need our checks and balances. We need to make sure that everything that is coming in is going out so we can balance this budget. For example, in India and China, most new energy generation since 2000 came from conventional sources, and their economies are growing. Their economies are growing very, very rapidly. And most of them, it's coming from lots of coal. China is trying to generate electricity through dams. They're not too big on nuclear right now, but they are trying for renewable resources as well. But it's very important that we try to keep the CO2 within our atmosphere as low as possible.